So we'll continue with group theory part. So this is lecture 3 now. In first lecture, we saw the definition of group and some examples like Zn, units of Zn. Then we saw symmetries of triangle and so on. And all these things, they can be generalized for any n, right? Then in second lecture, we saw like powers of element, then order of element, right? And some properties. But in fact, yesterday the time was little less. Instead of 1.5 hours, it was 1 hour. So we could not prove each and everything, or I mean, at least the important things. So today we have two lectures. So I'll try to be little slow, little more rigorous. We'll try to prove some theorems, some results also. Okay. And once again, since this is little abstract, maybe little new to you, right? You can ask wherever you have doubts, you can ask. Really, it's a small group and you are all talented. So you can even ask in between, no problem. Okay. So today, what we are going to do is substructure, that is subgroup. Okay. So generally in mathematics, everywhere we have certain structure and we also learn the substructures. Okay. So same idea here. We have the concept of subgroup.
Sir,
Yes.
sir, are we not proving those points we said yesterday, or are we supposed to prove it ourselves?
Yeah, they are simple results, and
Yes,
I
sir.
mean you can try to prove yourself also. Right? Uh, I, I,
Sure.
I don't think they'll be too difficult, and if at all needed, you can even look at any standard book also. So once we know the concept of like order of element, they are all small
Sure.
results. So there was as such no big result in those things. Right? So try to prove as far as possible. Okay. Yeah. Yeah. So we'll start with the subgroup concept of subgroup. And essential idea is a subset which is itself a group, and that's called as subgroup. So let's see the precise definition. Let J dot. Now I'm using dot. Once we are used to the concept of group, every time there is no need to use star, etc. Generally, we use multiplicative notation. So let G dot be a group. Let H subset of G be a non-empty set. If H is itself a group under the same operation restricted to H, then we say H is a subgroup of G. And generally, notation which we use for subgroup is it's a little different from subset. It's like H less than or equal to G. So, I mean, we don't call less than or equal to G, but as H subgroup of G. Okay. So, that's the notation for subgroup. So we'll try to understand definition again with examples. Since the subject is abstract, try to do as many examples as possible. Examples will clear various results, various definitions, etc. So let's see some standard results and then we'll understand this definition again. So idea is following, like under addition, we know Z is a subgroup, Z is a group, right? Rationals under addition is a group. Okay. Now we see that Z is non-empty subset of Q, right? It's a subset of rationals. Okay. Now, if I give you, like, say, for example, 1 and 2 belonging to Z, then 1 and 2 also belong to Q. They are also rationals. And as element of Q, whatever is the addition, same answer we want even in this set. That's what we mean by operation restricted to H. So we are saying the same operation restricted to H. So operation is same. I mean, whatever is addition of two elements or whatever is product AB in G, same is going to be answer in H also, right? So operation is same. Only thing restricted to H, which means essentially. So when I talk of Q plus is a group, here actually we have plus is a binary operation from Q cross Q to Q. It's two rationals, and as answer what we get is again some rational. Now instead of that, when we look at Z plus, I'm looking at basically same function, but I mean same operation, but now my domain set is different. So I'm looking at it as from Z cross Z to Z. Is that right? So you look at two elements AB. What I mean by same operation, so these AB are also elements of Q, and as elements of Q, whatever answer I have, same answer I want here, or same thing I'm defining here. So that's what we mean by operation is same. Okay. So in this sense, now we can say Z plus is a subgroup of Q plus. Is this fine? Is this clear? So maybe I can go to definition once again. So H is subset, right? So original operation is from G cross G to G. So I have same operation essentially, but now I look from H cross H to H. Right? So H should be closed basically under the same operation. Right? So dot is from H cross H to H. Right? And then if H itself is a group under the same operation, then H is called as a subset, which is itself a group, and that is called as subgroup.
Sir,
Yes.
sir, so the set of rational numbers under addition will be a subgroup of set of real numbers under addition, no, sir?
Very good. Yeah. So
Okay.
now we can see some such various relations. So on same lines, I can say now Q plus. Right one. Yeah, I can say Q plus. In fact, let's go step by step. So Z plus we said is a subgroup of Q. Is that fine? Once again, you remember it this way. This is a group. This is a non-empty subset, and this is itself a group, and the operation is same. What I mean by operation is same, essentially, whatever. So you look at any two elements of Z. So they are also elements of Q, and as elements of Q, whatever is answer here, same answer we want here. That's what we mean by same operation. Okay? Yeah. So Z plus is subgroup of Q plus. Now I can say similarly Z plus is subgroup of R plus. Right? I can say on same line Z plus is subgroup of C plus, or as you said, we can say Q plus is a subgroup of R plus. Right? You can say Q plus is a subgroup of C plus. Right? We can say R plus is a subgroup of C plus. Is that fine? Okay. Now, similarly, we can talk of even like multiplications. So, for example, Z star is not a group, but Q star is a group. So, Q star dot, you can say, is a subgroup of R star dot. Q star dot, even I can say, is subgroup of C star dot. We'll see some more nice examples of subgroups of C star today. Then similarly, I can say R star dot is a subgroup of C star. All of you fine up to this? Even I can say, like, if you want finite examples, if I take plus minus 1 under multiplication, then that is going to be subgroup of each of them, like Q star, right? C star, R star, everything, right? Yeah. Shall we go ahead?
Yes.
Any doubt? Any doubts? So, I mean, you can remember it this way, right? It should be subset. It should be itself a group. Operation must be same. Then that is a subgroup. Now, let me tell you some little tricky examples. Like one is from matrices, but since some of you don't know matrices right now, I'll avoid that the example. Maybe while doing this doubt session, I'll give that example. But let's see one more example. Like look at Z10. So what we mean by Z10? So numbers modulo integers modulo 10, right? So we have classes of reminders 0 bar, 1 bar, 2 bar up to 9 bar, right? Now we know under addition it's a group, but under multiplication this won't form a group, right? The trouble is, in fact, the inverses, right? Every element may not be invertible, and we know in fact which elements are invertible. But look at this set. So if I take x equal to, say for example, 2, then I can include 0. Or better, let's see what happens with this one. 2, 4, 6, 8. Okay, let's see what happens. So if I form table modulo multiplication modulo 10. Yeah, so what's the table? 2 2s are 4, 2 4s are 8, 2 6s are 12. We are working modulo 10, 2 8 the 16. I hope all of you are following. Then 4 4s are 16, 4 6s are 24, 4 8s are 32. Again, what I get is 4 and 2. It's commutative. So whatever is row, same is column. 6 6s are 36. Right? 6 8s are 48. 8 bar, and 8 8s are 64. Now, do you see every element occurs in each row, each column exactly once, right? It's associative also, and therefore this will form a group. So this is a group under multiplication modulo 10. Is that okay? Right? But this is not a subgroup of this, because original one under multiplication is not a group. Right? Now here, what is the identity? What do you see? What is the identity? This forms a group because it's like every element occurs in each row, each column exactly once. What will work as identity? Now, usually in our mind for multiplication, we have 1 bar, but in this case, there is 1 bar is absent. But do you see like 6 bar, as someone said, that is identity, because 6 bar into every element is itself 2 bar into 6 bar is 2 bar, 4 bar into 6 bar is 4 bar, 6 bar into 6 bar is 6 bar, 8 bar into 6 bar is 8 bar, right? So 6 bar works as identity. So this is a group, but I mean, it is in itself a group. It is not a subgroup. Is this point clear to everyone? Because original is not a group under multiplication. Is that fine?
Yes, sir.
Yeah. So in fact, if at all I want to look at multiplication modulo 10, in fact, the original group was something like this. So it was like 1, 3, 7, 9. That forms a group under multiplication modulo 10. And there is no connection between this and this, because in fact, neither is subset of each other. In fact, no element is common also, right? So this is totally different. So that's a tricky case, right? Where you see like under multiplication modulo 10, some subgroup of this, some subset of this forms a group, but that cannot be called as a subgroup. Is that fine? So far clear? Yeah. And in fact, this point I want to stress a little more. So in fact, what one can show is, if at all H is subgroup of G, if H is subgroup of G, so I know H is itself a group, right? And therefore H will have identity. G also has its own identity. What one can prove is, then identity element of G is just same as identity of H. So identity element of H is going to be same original identity of group. Okay. So we saw, in fact, such rigorousness we saw even in the first lecture definition. Like identity, in the definition we said there exists identity, but later on, in fact, we proved rigorously that identity is unique. Right? Similar things happen. So nowhere I'm saying that identity of H must be identity of G. I'm just saying H should be subset of G, right? Under the same operation, it should be itself a group, right? And we saw, in fact, it can happen like H is subset of original thing, right? But something different may work as identity, right? So we want to, but here the example was like this is not a group under multiplication, right? So uh, identity may turn out to be different. But once G is group, H is subgroup, the identities must be same. Okay. So let's try to prove rigorously. So this is H, this is G. And whatever is identity element of G, I want to claim that it is in fact inside H. And once it is inside H, identity of H will be just essentially same, right? So let's begin with, suppose E dash is identity of H. And E is identity of G. E is identity of G. Okay. So what can I say? If I choose any element of H, let me choose any X in H, any X. So then for any X in H, what I have is X into E dash. I'm not using star. X into E dash is X. E dash into X is X. Is that okay? This is working in X. But note also, if X belongs to H, then that X also belongs to G. All right. So X belongs to G also. And as element of G, what I can see is X into E will be X, and that will be equal to E into X. And now try to understand the point. In fact, both these equations I can look at as now in G, right? Because all elements are ultimately in G. Operation is same, right? H is group under the same operation, right? So operations are also same. Now I can look at these two equations as equations in G. So what happens? I can say now like X into E dash is equal to X into E in G. I'm looking at both the things now in G. Is that fine? I mean, operation in H is same as operation in G. So this also holds true in G, and this is obviously true in G. I can look at both equations in G. I have X E dash equal to X E in G. But what will happen? So I can multiply both sides by inverse of X in G. So in some sense, we have cancellation laws in G, right? Using cancellation law, or to be very precise, multiply both sides by X inverse and use associativity, right? So cancelling X from both sides, what we'll get is E dash is equal to E, right? So what I get is ultimately, though I started with suppose E dash is identity of H and E is identity of G, ultimately what we get is E dash is E, right? So in fact, the identity elements are same. So this itself again indicates, like for example, so for example, surely I can say like H is subset of Z10. On both sides, I have operation of multiplication modulo 10, right? But the here identity is 6 bar. Here identity will be like 1 bar. If I multiply any element by 1 bar, answer is itself. And this clearly indicates this cannot be a group. It can't be a group. Because if at all it's a group, then this is a subgroup. And then the identity element of subgroup and a group, that must be set. That's another way to look at this, that Z10 under multiplication modulo 10 cannot form a group. Is this point clear?
Yes, sir.
Yeah. Okay. So let's go ahead. Fine. I'll give one or two more examples. Like maybe if you can keep the multiplication table of D3, right, it's also called as S3. So if you keep table of D3, observe like D3 is symmetries of equilateral triangle. So maybe you can keep it handy. We'll use it quite often. Take the first part, like for example, if I take just these three elements, check this part of your multiplication table, Kelly table. This is row naught, this is row 1, this is row 2, this is row 1, this is row 2, this is row 2, this is row naught, this is row naught, this is row 1. Check. So do you see, like under the same operation, right? This is close. Uh, every element occurs in each row, each column exactly once, and which means essentially this part, do you see itself is a group? Is itself a group? Right? It is self-sufficient. It's close. We have identity. We have inverse. Everything. Right? So this will turn out to be subgroup of D3. Right? So row naught, row 1, row 2. This is subgroup of D. Okay. Or similarly, you can check just this one. You can quickly form a table. You can form a table, construct a table, row naught identity and mu1. Note, identity is necessary element of subgroup because it is itself a group. And now we have also claimed or we have proved identity remains same. Original identity of G will be also identity in H. So I need the same identity element in subgroup also, right? So one sure element of subgroup is identity, right? Yeah. So take row naught mu1, check whether it's a subgroup of D3, check the table. This is row naught, this is mu1, this is mu1, and mu1 into mu1 is again row naught. So it's close, right? Every element occurs in each row, each column exactly once. So that is itself a group. So it's a subgroup, right? But for example, if I take a row naught mu1, mu2, check that won't form a subgroup. Check mu1, mu2. Check what happens now. This is row naught, mu1, mu2, mu1, mu2. This is rho naught, right? This is rho naught. Look at what is mu1, mu2. What is mu1, mu2? That is something like row 1. Do you have table with you? Check, this is row 1 and this is row 2. Check.
Sir, mu1,
One
mu2
second,
is row
sir.
1.
Huh?
mu1, mu2 is row 1, sir.
Yeah. So mu1, mu2 is row 1 and mu2, mu1 is row 2, right? But do you see now the set won't remain closed under the operation? My set is rho naught, mu1, mu2, and when I multiply two elements, I get something outside the set. So it is not at all closed under the operation. So it cannot form a subgroup. Is that right? This can't be a subgroup. Right? For the reason because I get some elements which are outside the set. So that is not a subgroup. Are you getting the point?
Yes, sir.
All of you can freely ask doubts. This is something abstract, maybe a little new. Is this okay? That this is not a subgroup. Fine. Why? The trouble is it is not at all closed under the operation. Right? I get something as product which is outside the set. So it can't be a group. Right? Yeah. So So something like rho naught mu1 is a subgroup. Now you see by symmetry, I can have something like rho naught mu2 is a subgroup, right? Has something like rho naught mu3 is a subgroup, right? This is subgroup rho naught rho1 rho2, right? But this won't form a subgroup, right? Let's talk of even Klein 4, which we saw yesterday. What was Klein 4? So it was abstract group with 4 elements, and many 4 order elements, their behavior is something like Klein 4. So for every element, square is identical, right? Now, if I look at just say E and A, check whether this is subgroup, or if I give you something like EAB, check whether it's a subgroup. You can form a table. If it is itself a group, that is a subgroup, right?
Yes,
this
sir.
form a-
EA is subgroup.
Yeah, this is E, this is A, this is A, and A square is identity. That's our definition. So fine, it's closed under the operation, right? And every element occurs in each row, each column exactly once. So fine, this is the subgroup, yes.
Sir, no.
Yeah.
Maybe it's-
Hello? Yeah. So what about second one, EAB?
No, sir. AB is
EAB is not a subgroup,
Yeah,
sir.
so EAB is not a subgroup, right? So the trouble is with product A and B, right? If I take particularly A into B, that is C, B into A, that is C. So we get something outside the set, right? So this is not a subgroup. Fine. I hope this idea is clear. Then I want to do one standard example from C star. And that's important. So nth roots of unity. Again, we'll do first special cases and then I can say a more general case. So far, fine. Can we go ahead? Shall we go ahead?
Yes, sir.
Yeah. So I want to talk about nth roots of unity. In fact, they form a group. So group of nth roots of unity. So I'll do a little slow. All of you know complex numbers and basic operation like multiplication, etc. Right? Or shall I recall? Shall I revise? You can freely say whatever you want. Right? So if you are knowing complex numbers, basic complex numbers like addition, multiplication, then that's enough for us. So if you don't say anything, I'll assume that you know the things. Is that okay? Is that fine?
Yes, sir.
Yes, sir.
Yeah. If you want, you can write down in chat box. Yeah, Arjun. Yes, yes. Okay. So essentially, I look at, like, for example, say x square equal to 1, right? Or more generally, if I say, for example, if I say x square is 2, then we say x is with sign plus or minus root, right? So we say this is square root of 2, right? Or if I say x cube is 2, so I'll say x is cube root of 2. And more generally, if I say x raised to n is equal to, say, some number a, so I'll say x is nth root of 2. Now, if a is 1 in particular, we'll call it as nth root of 1 or nth root of unity. As simple as that. Okay. So I'm essentially going to talk about the numbers for which x raised to n is going to be 1. And let's see step by step. Like suppose x square is 1. All right. Then this will have 2 roots. Right. it's a degree 2 polynomial, so this will have 2 roots in C. Or essentially, right now we want to talk in C because anyway it's not going to be 0. If I look at x cube equal to 1, this will have 3 roots in C. If I look at x raised to 4 equal to 1, this will have 4 roots in C star. Note, we may not have all 4 roots in R, right, or R star, but we have all n roots in C star. That's a result by Gauss. It's known as fundamental theorem. Every degree n polynomial with coefficients in C has a root in C, and essentially then applying it again and again, what we get is we have exactly n roots in C. Okay, so that's the result due to Gauss. In fact, that was his PhD thesis, the fundamental theorem of algebra. Okay. And he completed it very early, I think at the age of 22 or something, because his first book got published when he was 23, 24 years old. Fine. So in general, x raised to n is equal to 1. We'll have n roots, right, in C. There will be n solutions. And those n solutions form a group, itself a group. And original group is C star. This is again a subset, which is itself a group. So it's going to be a subgroup, right? So they will form, in fact, a subgroup of C. Right? That is the idea. But we'll do some particular examples, and then we'll say something more general about x raised to n equal to 1. Okay. So let's quickly see, like, suppose x square is equal to 1. So we know what are the roots. X is equal to plus minus 1. And we have already seen plus minus 1 forms a group under multiplication. Under dot is a group. Is a group. Okay. Look at x raised to 4 equal to 1. So what are the roots? X raised to 4 equal to 1. I can say x raised to 4 minus 1 is 0. X square minus 1 into x square plus 1 is 0. And now you can easily see all the 4 roots. So what are roots?
Sir, plus 1 minus 1.
Yes, that will be from this. Right? X square minus 1 is 0 means x is plus.
Or I means square root of minus 1.
Yeah. Do you agree? X square. So either this is 0 or this is 0, right? So if this is 0, it will give me x equal to plus minus. And if x square plus 1 is 0, then which means what I get is x square is minus 1. So that's why I asked whether you know basic things of complex numbers or not. So this will give me what? Like root of minus 1 with plus minus sign. And root plus minus, I mean that root of minus 1 is defined as or is denoted by I, right? So it's basic imaginary number, right? So plus minus I. So what I get is 4 roots. X raised to 4 equal to 1 has 4 roots. 1 minus 1, I minus I. And you check the multiplication table. Quickly you can have multiplications. 1 minus 1, I minus I. And see that this forms a group under multiplication. Can you do that? If anyone has problem with complex multiplication, you can ask me what are doubts. If you are knowing, I mean, this is something too basic, like I into I is minus 1, etc. So I hope even if you know very basic things about complex numbers, you can do this.
Yes, sir, done.
So obviously, one is going to be identity, so I can fill up this. And once I know operation is commutative, you can fill up row and same will be the column. So you can even simultaneously fill the column or row, right? right? So 1 minus I plus I minus I plus I. Then I into I square is minus 1. I into minus I will be plus 1. This is plus 1.
Minus 1.
This will be minus 1, right? Check that every element occurs in each row, each column exactly once, right? And it's a group. Is that fine?
Yes, sir.
So even fourth roots of unity form a group, right? Now let's go to cube roots of unity. So x cube equal to 1, or it's like x cube minus 1 is 0. Find out the three roots. Now, as compared to x raised to 4, it will be little involved, right? So we have to find them little precisely.
Sir, all three will be 1, right?
No.
So there's the x squared minus x plus 1 term.
See, if all three are 1, essentially I won't get x cube minus 1, I'll get x minus 1 cube. Then I'll get all three will be 1, 1, 1, right? And this equation is going to be different than this. This will give me something like x cube minus 3x squared plus 3x minus 1 equal to 0. Then you can say all three roots are minus 1, 1, 1. But this is something different. But one thing is sure, like 1 is always going to be root. Is it right? 1 is going to be root.
Sir, is it 1 plus or minus 3i by 2?
Yeah. So in fact, yeah. So in fact, 1 is going to be one root, and the other factor you can find out. Even you can find by what is known as synthetic division, right? I
So
hope.
Ignatius quadratic formula.
Yeah. So I hope all of you have done this synthetic division in schools, right? Maybe 8th standard, 9th standard. So this is 1. And get to 1. 0 plus 1 is 1. 1 into 1 is 1. 0 plus 1 is 1. 1 into 1 is 1. I get last part is 0. So it's a perfect division. And your quotient is given by this. So that is x squared plus x plus 1 equal to 0. Now I know this, either this is 0 or this is 0. If this is 0, my x is going to be 1. And this is quadratic. We know how to find roots of quadratic. What is the formula for roots of quadratic? What is the formula for roots of quadratic? Like say
Minus b plus or minus 1.
yeah, minus b plus minus root of b square minus 4ac upon 2a. And in this case, luckily, everything is 1, 1, 1. So you can write down the roots. That will give you two other roots. And see that they are not real. They are essentially imaginary, right? Complex. So it's 1 minus 4, that is minus 3. Right? So shall I say it's 1 and minus 1 plus I root 3 by 2 minus 1 minus I root 3 by 2. Okay. Now your job is to check whether this forms a group or not. So we want a table, multiplication table. 1 minus 1 plus I root 3 by 2 minus 1 minus I root 3 by 2 1 minus 1 plus I root 3 by 2 minus 1 minus I root 3 by 2. So I'll get 9 elements, right? 9 elements. And some elements will be obvious. Like when I multiply by 1, that's going to give me again. So 5 elements are something obvious, right? What about this element?
-1 minus I root 3 by 2.
Yeah. And see that you really don't have to multiply this. Note this and this. I mean, they are both roots of x square plus x equal to 1. Right? So essentially, x square is going to be minus x minus 1. So I don't have to really multiply these two complex numbers. Just take this minus 1. That will give me the answer. Is it right?
Yes, sir.
Okay. So check this answer turns out to be minus 1 minus I root 3 upon 2 from this equation. And once again, from same equation, if alpha and beta are the two roots of quadratic, then alpha into beta is c by a. So in this case, all ABC are 1, 1. So do you see this product has to be 1? It's a product of two roots, right? So this has to be 1. This has to be 1. Okay. And similarly, check second one. I mean, second product. Again, it's you don't have to multiply. It's minus x minus 1. And now hopefully we can guess, like, this has to be, if at all it's a group, it has to be that first element. So it should be, check, minus 1 plus I root 3 upon 2. You can check by, I mean, you can do it by minus x minus 1. I don't have to actually multiply two complex numbers. It's simple addition subtraction, right? All of you are clear up to this? And see that now once again in the table, it's closed. I get again elements from same three elements, right? Then every element occurs in each row, each column exactly once. So that is a group. But now we can see something more about same table. Let me call this element as W or omega actually. Okay, so I'm calling this as omega, or you may call it W or anything, right? Now, do you see, like, when we actually constructed the table, this element, I mean, W into W turned out to be this element. Is it right? Product of this element, I mean, square of this element turns out to be this third element. Is it right? So if I'm calling this as W, do you see this third element is nothing but W square or omega square, right? And now table becomes more easy. It's something like 1 W square, 1 W square. So it's 1, in fact, shall I call it omega? It's actually generally, I mean, Greek letter omega. Okay, so omega square, 1 omega square, omega into omega will be omega square, omega into omega square, that is omega cube, and omega cube must be 1 because it's a root of x cube minus 1, right? Similarly, omega square into omega,
Yes, sir.
that is this omega cube, that is again 1. And if omega cube is 1, what will be omega raised to 4? That is omega cube into omega. That will again turn out to be 1 into omega. So shall I say it's omega? Is this point clear? This table clear?
Yes, sir.
And now you can observe, in fact, not just with this table, in fact, I can see same thing with even earlier two tables. This -1, if I call as omega, -1 is like my omega, then it's like 1 omega, omega square is 1, right? So that's my table for 1 minus 1. And again, this, if I, instead of 1 minus 1, I minus I, if I take it as 1 minus 1, let me call I as omega, right? Then, in fact, check that this will turn out to be -1 will be like omega square. Is it right? -1 will be omega square. If I call this as omega, this is going to be omega square. And check, this will be again one more omega. So that is omega cube. So again, my table becomes something like 1 omega, omega square, omega cube. And I can construct the table. So this gives us some hint about the general nature, general structure of nth roots of unity. So now I can tell you the general structure of nth roots of unity. It turns out to be something like this. Looking at these first three examples, so the general structure of nth roots of unity is of this form. So I call that set as UN, nth roots of unity. So all complex numbers, z raised to n is 1. And essentially it turns out to be of the form 1 omega, omega square, omega cube up to omega raised to n minus 1. Omega raised to n is again going to be 1. Right? So how to choose that omega? That is, or what should be our omega? Like for example, in case of this example, I call this as omega. Even one could have called this also as omega. Still, the table works. Okay. But in case of like, for example, 1 minus 1, I minus I. I can't call this as omega because then I'll get only 1 minus 1. I won't get other two elements, right? So I have to choose, pick up proper element as my omega. Is that fine? And it turns out that, so it turns out that this omega turns out to be e raised to I 2 pi upon n. That is called as primitive nth root. Or I mean any element which gives me full un, all n roots, such a root is called as primitive n. Okay. Now what happens is following. I mean, why omega is something like this. So what I get is, in fact, it's based on Euler's identity. So this is well known. It's a very well known equation. E raised to I theta is cos theta plus I sin theta. This is Euler's identity. Okay, so in particular, if I take e raised to I 2 pi, what I get is cos 2 pi. Cos 2 pi is 1, sin 2 pi is 0. So what I get is, this gives me 1. Okay, in fact, a special case of this is also well known. That's supposed to be one of the most beautiful formula in mathematics. So if I take e raised to I pi, that is cos pi. Cos pi is how much?
-1.
-1, and sin pi is 0, right? Sin pi is 0. So what I get is e raised to I pi is -1, or e raised to I pi plus 1 is equal to 0. And it's why do you see, I mean, the beauty of that? So like 0, additive identity, 1, multiplicative identity, right? I, basic imaginary number, and 2 well-known irrational numbers which we need here and there quite often, that is pi and e, right? So they all 5 are in fact bound together with a nice relation, right? So that's also known as Euler's identity, right? Okay. So once again, so omega, if I take as e raised to I 2 pi by n, then omega raised to n will be e raised to I 2 pi, and n will cancel. That will be 1, right? And once omega raised to n is 1, observe, even if I take omega square raised to n, that is going to be omega raised to n square, that is again going to be 1. Or for that matter, if I take any power of omega, right, that will again give me 1. Do you see that? Okay. Now, then if every power is going to be nth root of unity, why only n elements? Why not infinitely many? Luckily, what happens is you start like 1 omega, omega square, omega cube, every power of omega. After n steps, omega raised to again turns out to be 1. So they repeat, right? In fact, such a group we'll see tomorrow. Such a group is called as cyclic group. Okay. And this, I mean, the name cyclic comes from the very geometric nature. So if you plot them on a complex plane, say real axis, imaginary axis, they all lie on a circle of radius 1, the distance from origin is 1, and they divide the whole circle into n equal parts. So this first one dividing 2 pi by n. So angle is 2 pi by n. That gives me omega, and this gives me omega square, omega cube, omega raised to 4, omega raised to 5. So it divides the whole circle into n equal parts. This is omega raised to n minus 1. Omega raised to n is again 1. Omega raised to n plus 1 will be again omega. Omega raised to n plus 2 will be omega square, and so on. It's a cyclic thing, right? So they keep rotating again, right? So how many are distinct out of all these powers? So every power is nth root of unity, but how many will be distinct? 1 omega omega square up to omega raised to n minus 1. Is this structure clear to everyone?
Yes, sir.
Yes, sir.
So that's about nth roots of unity. And luckily, in fact, if I take union of all of them, even that turns out to be a subgroup. So again, I may not prove each and everything, but I can give you some idea later. So far fine. So we defined subgroup, right? Then we saw like identity must be same. Then we saw some nice examples, and now the main example in groups of unity. So what can I say now? UN is itself a group, and it is subset of complex number C star. So I can say UN is a subgroup of C. Is that fine? Okay. So shall we go ahead?
Yes, sir.
So criteria, necessary and sufficient condition for something to be a subgroup. So H should be non-empty, right? And then it's a subgroup if and only if AB inverse belongs to H. So maybe I can explain the condition. I may not write rigorously each and everything, but I can explain the condition. So note, if H is subgroup of G, then it means H is itself a group. H is itself a group. And then if I take A, B belonging to H, right, then I know once B belongs to H, B inverse also belongs to H because it's a group, right? And once B inverse belongs to H, again by closure property, AB inverse. So one way is obvious, like if H is subgroup, that implies this one. That is obvious, right? Conversely, suppose we have the following condition, like whenever AB belongs to H, the converse part, whenever AB belongs to H, it implies A into B inverse belongs to H. That is given. But again, note this is little tricky. What do I mean by I want to prove H is subgroup? So, right, I'm not given H is subgroup. I want to show it is a subgroup. So what do I mean by then B inverse? Note H is already inside and G is a group, right? So even if I take two elements A and B from H, they are also elements of G. And as element of G, right, they have inverse. So the B inverse will exist, right? And right now, even I don't know whether B inverse is inside H. B inverse can be somewhere inside G, right? So it may be anywhere, but the condition says, in fact, A into B inverse, this product will come inside. That is what is given. Point clear? I'll say once again, H is not a group. We want to prove H is group, right? So I can't say B inverse directly belongs to H, or I mean, even I can't talk. If it is not a group, I don't know what is inverse, etc. Right? So, what inverse we are talking about? What do I mean by B inverse here? It's actually inverse of B as an element of G. And that surely will occur because G is a group. So that exists. So it will belong to G, and it can be anywhere in G. I don't know whether right now I don't know whether it is in H or not. It will belong to B in G. It will belong to G. So it's somewhere in G. But the condition says whenever two elements A and B are in H, right? A into whatever that inverse in G, this element, this product is again inside H. That is given. Okay. So if this is given, one can prove actually step by step that H turns out to be group. So once it's a group, it's a subgroup. Okay. Now idea is this. We are already are given that H is non-empty. So H is non-empty means what? There is at least one element, right? There is some X in H, right? Now by this condition, what I'll take is this is for every AB belongs to X. You take any elements AB in H, condition holds. AB inverse belongs to X, right? And nowhere we have said that AB are distinct. We haven't said any such thing. So I'll take A as X, B also as X. So XX belongs to H will imply by condition X inverse belongs to H, but which means E belongs to H. So I get identity belongs to, right? Now I'll talk of inverse. Yeah, Arjun. So inverse exists already, right? And ultimately that gives me Okay, so E belongs to it. Fine. Now I'll show that inverse also belongs to it. So I'll take now, already we have established E belongs to X. Take any element, say X belonging to H, then by condition, again, E into X inverse will belong to H. So which means now I can say whenever element is in H, its inverse also is in H. So that establishes contains inverse, right? And finally now, if A and B belong to X, so we have established even B inverse is also in X. And now I use the condition. What I get is A into B inverse will again belong to H, right? By condition. So I'm applying condition not to A and B. I'm applying this condition to A and B inverse. So A into B inverse will belong to H. But that gives me AB belongs to H. So in fact, this gives closure property. So H is closed, right? H contains identity. For every element of H, inverse again is inside H, and associativity follows. I don't have to prove. They are all inside G. So associativity follows from that in G, right? So which means H is itself a group. So H is that fine? So this is the criteria for showing something is a subgroup. Okay, and again I'm going to show you one important example, the subgroups of Z. Okay, and then what if at all we are left with some time, I'll comment on various problems one in the chat. Okay, so we'll first try to complete the example of subgroups of Z. Okay, now let me just comment here, remark here. If the group is, I mean, all these things are with multiplicative notation. If the group is additive, instead of A into inverse of B, what I'll say is A plus inverse of B. And inverse of B in additive case, we denote by minus, right? So as far as additive notation is concerned, what we have to prove is H is subgroup of G if and only if A minus B belongs to it. That is the criteria with additive notation. With additive notation. Okay, so shall we go ahead and prove examples of subgroups of Z integers?
Yes, sir.
Any doubt?
No, sir.
Okay. So again, first part you work, and then the main part, second part I'll work. Okay. Again, I'll try to be as rigorous as possible. Sorry. Okay. So our group is Z. It's group under addition. Operation is addition. Try to show that 2Z, I mean, all even numbers, okay, forms a subgroup. So you try to prove this one by our criteria. Okay. So prove 2Z is a subgroup. Fine. And now I'll just comment. Once you prove 2Z is a subgroup just on same lines, I mean, nothing special about 2. One can show 3Z is a subgroup, 4Z is a subgroup, or more generally, one can show every MZ is a subgroup. Okay. So just you have to replace 2 by M. That's it. Okay. So you try to prove 2Z is a subgroup. So take 5 minutes.
So can you repeat the question, sir?
Yeah. GZ, Z is group under addition, and I'm giving you subset H equal to 2Z. So what I mean by 2Z? All even numbers. All even numbers. And I want to show that even numbers
Oh, yes.
form a subgroup of G, or I mean multiples of 2 form a subgroup of Z. And I'm saying nothing special about that 2. Instead of 2n, I can prove all multiples of 3 form a subgroup, all multiples of 4 form a subgroup. In fact, in general, subgroup is MZ. Okay, MZ is a subgroup.
Yes.
So your criteria is following. So you have to just see that, observe that H is non-empty. Just ensure that it is non-empty. And whenever AB belongs to H, you have to prove A minus B, because this is additive notation, belongs to H. That is what you have to prove. So why it is non-empty? In fact, you see there are infinitely many elements. So absolutely no problem to see that or claim that it is non-empty, right? Any multiple of 2 is going to be inside H. So do you see like 0 obviously belongs to H. So I can say H is non-empty, right? Or I can say 2 belongs to H, right? So H is non-empty, or in fact H has infinitely many elements, right? So that is no problem. Okay. If I start with some AB belong to H, what can I say about nature of A and B? Can I say can AB1 or can AB3, can AB5? That is not possible, right? So AB both are out of 0, plus minus 2, plus minus 4, plus minus 6, and so on, right? So what can I say about structure of A and B? What can I say about A? Shall I say it is of the form 2 times something,
Multiples of
2 times something, right? Multiple of 2. And similarly, B will be also 2 times something. But then, if I look at A minus B, that is 2 times K minus 2 times L, which is again 2 times some integer. What integer? Integer minus integer. K minus L is again integer. So shall I say A minus B again belongs to H?
Yes, sir.
Yeah, so that means 2Z is a subgroup. Now you see, in fact, rule of 2, like essentially just we use it here, like 2 times k, 2 times l. Now instead of that, if you say 3 times k, 3 times l, I'll get 3Z is a subgroup, 4Z is a subgroup, 5Z is a subgroup, right? So all MZs are subgroup. All of you are convinced? MZs are subgroup. I can have m equal to 0 also, because if I take 0, I get just singleton 0, and that is identity. Identity is always a subgroup, right? If I take m equal to 1, I get full Z, and every group is always subgroup of itself. In fact, just identity is called as trivial subgroup. That is always a subgroup. That is trivial, and whole group is again obviously subgroup. What is subgroup concept? It should be non-empty subset, I mean subset, and itself a group. So just identity we saw in very first lecture is a group, and whole G is a group. So these two are always subgroups, right? So this is called as trivial subgroup. This is called as improper. Improper. Anything strictly smaller than G is called as proper. So this is improper the subgroup. This is trivial subgroup. Okay. So anything which is between E and G, that will be called as non-trivial proper. Okay. So if I take m equal to 0, I get trivial. If I take m equal to 1, I get improper whole set. And if I take 2, I get even. These are multiples of 3, multiples of 4, multiples of 5, and so on. I'm not taking -1, -2 separately. Do you see -1 times Z is same as +1 times Z? Do you agree with that? Or -2 times Z is same as 2 times Z? All of you agree with that? Like what is Z? Z is, suppose I ask you Z. So Z is like 0, 1 minus 1, 2 minus 2, 3 minus 3, and so on. Now if I ask you -1 times Z or -2 times Z, right? So do you see -2 times Z will be what? I'll get 0. This side I'll get negative numbers, and this side I'll get positive numbers. But essentially this is same as 2Z. Is it right?
Yes, sir.
So Z and minus Z is same. 2Z and -2Z is same. 3Z and -3Z is same, and so on. So essentially, I need not take negative values of M. Either take positive or negative, one of them. That is enough. So I'm taking, for convenience, 0, 1, 2, 3, 4, and so on. Okay. Now the nice part is, in fact, what one can show is these are the only subgroups. There can't be any subgroup which is of different type than this. So every MZ is a subgroup, and every subgroup is a MZ. Okay. So even converse is true, and that's what we'll try to see. So conversely, if I take a subgroup of Z, yeah, let H be any subgroup of Z, we show H must be out of this only for some M. Okay, right now what I have proved is MZs are subgroups. That is fine. But does that mean that every subgroup is MZ? So that's what we want to show, right? There can't be any other type, like some elements here, some elements there, they won't form a subgroup, right? Essentially, if I start with a subgroup, again, it has to be out of these only. So this completes the list of subgroups of Z. Subgroups of Z are precisely all MZ type only. Is that okay? So are you getting the point? Like what we are showing now, right? Just now we proved MZ is a subgroup. Now I am proving every subgroup must be MZ type only. There can't be any other type. Are you getting this point?
Yes, sir.
And just let me try to be little rigorous here. because I mean, this is one important thing. So I start with subgroup. Possibly H can be trivial. So if H is 0, then no problem. So then I'll take M as 0. So H is 0. So H is of the form MZ in that case. So assume that H is not 0. So assume H is not 0. But H is not 0 does not mean that 0 does not belong to H. It means H contains elements other than 0. Are you clear? Subgroup means it must contain identity. And I'm saying H is non-trivial, so it is something more than 0. But it is not 0 does not mean it does not contain 0. This point is clear. 0 will be always there. Once it is a subgroup, it must contain identity. Identity is 0, so 0 will belong to H. But what we mean by H is non-zero is apart from 0, there will be some other elements. It won't be just 0. That is the meaning. Okay. Now, suppose there is some element K other than 0. So implies there exists some non-zero element such that K belongs to. But sorry, K belongs to H. Okay, H is non-trivial now. 0 case we have done. H is non-trivial means it contains elements other than 0, right? So there is some K other than 0. And do you agree? Because it is a subgroup, if K belongs to H, its inverse, its addition now, so minus K will also belong to H. Is it right? Minus K will also belong to H, right? But one of K and minus K must be positive. In fact, one will be positive, one will be negative. Exactly one of K and minus K must be positive. So my first claim that whenever some subgroup of Z is non-trivial, it contains elements other than 0, it must contain positive elements. That is first thing. Do you all agree with this? There can't be subgroup containing only negative elements, right? Because once element is there, its inverse must be present. And that is minus of it. So minus of it, right? So if one of them is positive, other will be negative. Other is negative, first will be positive, right? So do you agree that one of these must be positive? So H surely contains positive elements. And there is a nice property of positive numbers, right? If I take natural numbers or any subset of natural numbers. Any subset of natural numbers. Okay. Then one can always choose the least element. This you can't do over integers. From integers, I can't choose the least element because it may go to minus infinity also. But in case of natural numbers, always I can pick up the least element, right? That is known as well-ordering principle. Well-ordering principle. So WOP implies, well-ordering principle implies H will have least positive element. So we can have least positive integer. So which means out of various positive integers in H, I can always choose the one which is least positive integer. Let's call it M. Okay. And for this M, in fact, one can show that H turns out MZ. So for this M, we'll show that H is precisely MZ, right? No element can be something different. Every element of H must be multiple of M. That's what one can do. Okay, so let's see. Shall I go to next page?
Yes, sir.
So let's try to understand now. Now we want to claim that H is precisely MZ. Okay, so H will be MZ. That's what we want. One part is clear. Like once M belongs to H, right? Any multiple of m, like m plus m, m plus m, and so on. So any multiple of m will again belong to H, right? So any multiple of m belongs to H, which means every element of the form mz is inside H. So I can say mz is subset of H. That is one. And this is obvious. Main parties will show that every element of H is of the form mz. If I prove this, then 1 and 2 will imply that they are actually equal. Mz is subset of H, H is subset of mz. So 1 and 2 will imply H is equal to mz. Okay, so now I start with this one. So how to show H is subset of mz? So start with any element of H. So I'll take any X belonging. Okay, I want to claim it is element of mz. So I want to claim X must be of the form m times some k. Right? Then I can say X belongs to mz. If I prove X is mk, then I can say it belongs to mz. So which means any element of H I'm ending showing is element of the form mz. Right? So it will belong to mz. Now, what's best thing? So try to use general result. So if I divide X by M, I get some quotient K and some remainder. Is it right? This we have done right from our third, fourth standard, right? So that is division algorithm. So straight away divide X. So X is MK plus R, and I know there is some condition on remainder. What is the condition on remainder?
R should be less
It's
than.
less than k.
R should be greater than equal to 0. It can't be negative and strictly less than the divisor. So it's less than M. Is that right?
Yes.
Okay. Now see. So my claim is, in fact, claim R must be 0. And once R is 0, I'll get X equal to MK. Right? Once R is 0. Then that will imply X belongs to MZ. Now, why R should be 0? What will happen if R is not 0? Let's see. Suppose possible, R is non-zero. But if R is non-zero, then R will be positive, R will be less than M. And just see, because X belongs to H, because M belongs to H, right? And H is subgroup. Do you see their addition, subtraction will again belong to H? Inverse, everything will belong to H. It's a subgroup. So do you see, like this will imply X minus M K times, right? Will again belong to H. Is it right? X is from H, M is from H. So X minus M will belong to H, X minus 2M will belong to H, X minus any MK will belong to H because it is a subgroup, right? What is subgroup? It is itself a group. So which means it is closed under the operation. So you take two elements, right? Inverse, their addition, subtraction, everything will again belong to H. But if X minus MK belongs to H, that implies R belongs to H. Is it right? And do you see this is something contradiction? Why? Because R is positive by our assumption. R is less than M and it belongs to H. What we said, what was our M? M was least positive integer inside X. And now something smaller than M, positive belongs to H. Is it contradicting minimality of M? Right? We said what was M? M was least positive integer in H. That was M. And now something smaller than M, positive, belongs to H. That is a contradiction to the leastness of M. So why do we get contradiction? Our assumption is wrong. What was the assumption? Suppose R is non-zero. That is wrong. So what must be true? In fact, R must be 0. But once R is 0, I get X is MK. And that implies X belongs to MZ. And that will imply, in fact, that two things are equal. So now we are showing every subgroup of Z is essentially for some M, it has to be of the form MZ. Okay, I can repeat. So now we are showing subgroup of Z is MZ. So if H is just 0, fine, M equal to 0 volts. So assume that H is non-zero, non-trivial. And it does not mean it does not contain 0. It surely contains 0, but it contains something more than 0, right? So there is some element K in H, which is different from 0. That K may be positive, K may be negative. Okay. Now, if K is positive, fine. I want positive elements. I want to claim H contains positive elements, right? But suppose if K is negative, what will happen? Minus K is positive, and minus K again is inside H, right? So once K belongs to H, minus K belongs to H, and out of them, one must be positive, right? So very first thing, H must contain positive elements. It won't happen that H contains only negative elements. So H has positive elements, right? Then out of all positive elements, why I focus on positive, why not on negative? For negative, I don't have a result, but for positive, I have a result. Out of all positive number in natural numbers, I can choose least positive. That is called as well-ordering principle. So I can find out least positive element belonging to H. Suppose that is M. And then my claim is for this M, H must be MZ. Right? So every element of H must be multiple of M. And that's what we do by division algorithm. Is this one clear?
Yes, sir.
Now, very quickly, now we have just some 7-8 minutes left. Very quickly, I'll show one nice example of this Z itself. So, as I said, in fact, my whole aim was like to relate group theory and number theory. So, look at this nice thing. It's something simple. If I take, say, two subgroups of Z, say MZ and NZ. Okay. And if I add these two sets, then one can show that that is again a subgroup of Z. So what I mean by that, so take all elements of the form M times X and take all elements of the form N times Y. Right? M, N are fixed, right? They are fixed. X, Y vary. So I belong to Z. So I want to claim that this is again a subgroup of Z. Okay, I'll call this as H. Now, do you agree, first of all, 0 belongs to H? Because if I take X and Y as 0, 0 belongs to H. So H is non-empty. H is non-empty, right? Fine. Now you take any two elements from H. So let AB belong to H. So they are going to be what form? Implies A must be of the form M times some integer plus N times some integer. That is the structure of H. H is of the form all elements of the form MZ plus all elements of the form NZ. Right? I am taking addition of all such, every MZ type element added to every NZ type element. So all possible MX plus NY. That is my H. So A is going to be of the form MX1 plus NY1. B is again going to be of the form MX2 plus NY. And by commutativity, etc., I can say that A minus B will be again M times some integer plus N times some integer. I have commutativity, abelian group, right? So A minus B is this, and which means, shall I say it again belongs to H? It is M times something plus N times something. So it is again of this form. So shall I say A minus B belongs to H? So H is non-empty, and whenever AB belongs to H, A minus B belongs to H. Is it right? But that means what? Essentially, that means what? What we get? H is essentially subgroup of Z. Right? But if H is subgroup of Z, just now we have proved every subgroup of Z must be of the form some multiple of Z. I mean some MZ type. Right? So shall I say implies H must be some DZ type for some integer D. For some D. In fact, D will be positive, right? It can't be 0 because I will assume that Mn are not good 0. Okay. So assume Mn are not good 0. So D will be positive, right? So I get H is of the form some DZ, right? but which means I have got dz equal to mz plus nz. dz equal to mz plus nz. So if I have some subgroup mz, if I have some subgroup nz, if I add those elements, every element here with every element here, then that is again a subgroup, and therefore it must be of this form, right? Now, comparing the two sides, you can show that D divides M, right? D divides N, right? Why? Do you see, like M is equal to M into 1. That belongs to Z, right? So I can write M as M times 1 plus N times 0. So it belongs to dz. It is of this form, mz plus nz. So it belongs to dz. And once it belongs to dz, it must be of the form d times some integer, right? So d divides m, d divides n, right? And if at all any other c divides m, c divides n, that will imply, in fact, C will divide any combination. But you see, in fact, D is D times 1, so it belongs to dz. So D must be of the form, sum mx plus ny, right? So if C divides m, C divides n, that will imply C divides mx plus ny. But my D is going to be the form mx plus ny for some integers x and y. So C divides D. And that is your definition of GCD. Right? So GCD is defined by this method. Take MZ, take NZ, then MZ plus NZ is again a subgroup of Z. So it must be of the form some DZ. Then that D is defined as GCD. Okay, and in fact, now we don't have to separately prove Bezo's theorem. By very structure, in fact, what I get is D can be expressed as linear combination of M and N. This is in fact Bezo's theorem, right? So some such things can be done using group theory. Okay, sorry, Bezo's. Yeah. So once again, we defined subgroup, right? We saw criteria for showing something is a subgroup, right? We saw examples of nth roots of unity, and we saw, in fact, example of Z, I mean subgroups of Z, and lastly, like how GCD can be defined and how we see Bezo's theorem via group theory. Like GCD can be expressed as linear combination of those two numbers M and N. Okay. I think we can stop here. There are 2 minutes. If you have doubts, you can ask. We have one more lecture today, and in that lecture, I will continue with the cosets of subgroup. And again, I'll try to see if I can prove Fermat and Euler's theorem via group theory. Okay, so let's try to do that in the afternoon, 2:30 to 4. Still, there are 1 or 2 minutes. If you have some doubt, you can ask.
Sir, I have a doubt. Can you go to the slide of the converse of the criteria?
Yes. This one?
Not this one, the other one. The blue slide. One more.
Oh, achha, that one.
Yes, over here. Over here at the bottom right corner, how did you get the conclusion that E into X inverse belongs to H?
Yeah. Okay. So we have claimed because H is non-empty, we have claimed first of all using this criteria that identity belongs to it, right? Identity belongs to it.
Yeah.
Now, instead of those A and B, I mean, A, B are any elements of X. So now you take any element X belongs to H, and you also know that E belongs to H. So I'll take now E and X belongs to H. But once E and X belong to H, by criteria, E into X where X inverse will belong to H by criteria.
Oh, okay.
So I get X inverse belongs to H.
Okay. Yes, thank you.
Yeah. So shall we stop then? I'll stop sharing. We'll continue in the afternoon, 2:30 to 4.